This is a presentation of Group 12. Our topic is blockchain security and scalability. Blockchain is a decentralized and immutable free structure widely used for virtual currencies. Since blockchain technology is underlying rock of the virtual currencies, its security and scalability gain wide attention in recent years. The basic security of blockchain is guaranteed by hash functions and asymmetric encryption. Due to one-way property and collision resistance, hash functions are widely used to construct blocks and confirm the integrity of transactions. Asymmetric encryption uses public and private keys to encrypt and decrypt messages, and uses digital signature to ensure the basic security. We will introduce blockchain in the following four aspects. A smart contract is a digital protocol that can be executed automatically according to rules, and it was proposed by Szabo in 1994. The blockchain has made a smart contract active again, which is considered to be another popular technology. One example that makes the best of smart contracts is ETH. Most of smart contracts in blockchain control a huge amount of digital fortune, which are prone to be the target of hackers' attacks. The operation of a smart contract is not reversible. Therefore, attacks against smart contracts will lead to remarkable damage. Normally, the blockchain can only operate the data on the blockchain. In order to access external data and contact to it needs to rely on a trusted technology to do so. For example, Augur uses a special penalty mechanism to secure connections. Besides, the programming language of ETH is not mature. To solve these security issues, different verification tools for these smart contracts need to be introduced. Tools such as Remix can be used for validating and patching. The details will be introduced in the report. Due to the transparency of blockchain, privacy security also become a key concern. Smart contracts contain users' accounts and transaction information, so its privacy security is important. Cryptographic techniques can effectively ensure privacy security. For example, zero-knowledge proof allows sharing encrypted private states to everyone to hide users' identities. And prediction schemes of smart contracts are also popular. For example, Ekiden, which combines blockchain and trusted hardware to implement a smart contract platform to protect privacy. The details of these technologies will be described in the report. In Ekiden, please use input to create contracts. Computer nodes execute requests from the clients with contract TEE. Consensus nodes maintain an append-only ledger.
Consensus protocols solves the problem of inconsistency between multiple nodes in a distributed system. The unreliability of nodes and the instability of internode communication lead to the problem of inconsistent data between nodes. Consensus protocols can help distributed systems to achieve consistency and improve the reliability of the system. Proof of work is the first successful decentralized blockchain consensus protocol, where proof of work requires node participants to perform computationally intensive tasks, but is easy to verify for other participants. However, there are drawbacks such as large power consumption for mining and low transaction throughput. Proof of stake is an alternative solution to solve the resource waste and security defects of proof of work. Proof of stake only relies on internal coinage and equity, without consuming external computing resources, which fundamentally solves the problem of resource waste of proof of work. Security is one of the main issues of blockchain. Blockchain based on proof of work mainly faces 51% attack problem, which means that nodes have the ability to successfully tamper and falsify blockchain data by holding more than 51% of the computing power of the whole network. The proof-of-stake-based consensus solves the 51% attack to some extent, but also introduces the nothing-at-stake attack problem when the blockchain is forked. Nothing-at-stake attack is an attack against proof of work, which is not easy to detect and prevent. Theoretically, both proof of work and proof of stake based public blockchain systems can be subject to nothing-at-stake attacks. Many consensus mechanisms address this attack by introducing slashing as a penalty mechanism to discourage malicious behavior in order to build a more secure network. A Sybil attack uses a single node to control a peer-to-peer network by operating many active fake identities or Sybil nodes on the slide. When fake nodes are more than real nodes, the attacker will achieve domination of the blockchain with a vote lead. In this case, the attacker has the power to dictate the entire blockchain and can tamper with the transaction records and order, causing catastrophic damage. Blockchain technology is able to address Sybil attacks using different consensus mechanisms, such as proof of work. In proof of work used by Bitcoin, a node must finish a large number of calculations to prove its legitimacy and thus are able to change the block data. This is too costly for a Sybil attacker and not as cost-effective as being an honest and legitimate node. Another solution is authentication, which will be discussed in the report. What's next is a discussion of scalability of blockchain.
The importance of scalability in blockchain is indisputable. Along with the rate of popularity of blockchain application scenarios, the phenomena of blockchain network constitution receive more attention. It is impossible to bypass the critical paradox of blockchain, namely decentralization, scalability, and security, which can be only two of three. In this section, we will focus on the improving scalability, which has little impact as possible. The two virtual concurrency with a huge user size, Bitcoin and Ether, represent the urgent need for the blockchain expansion. Bitcoin currently has a TPS of only 3.51, so it became increasingly concentrated with a huge number of user transactions. Ether has not escaped the dilemma accountable by the Bitcoin, as the various tasks that required transactions using Ether increasing. Ether's TPS also become unbeatable. The current TPS of blockchain can no longer support the growing demand for the transactions, and it's become increasingly important to improve the scalability of the blockchain. The current mini-stream scaling solutions are mini on-chain scaling and layer 0 scaling. On-chain scaling is meaning to improve the scalability by optimizing improving the basic protocol of the public chain, which indicate the improvements to the data layer and the network layer. Data layer can be improved by the block expansion, isolation verification, and DAG. Block expansion is achieved by increasing the capacity of the single block so that the number of the transactions. Isolation verification increases the number of transactions. A single block can be hold isolation digital signature for the other transaction data, and the DAG allows for the high concurrency by avoiding the time wastage due to the data concurrencies and the network latency. The network layer is improved by scaling the blockchain into multiple pieces and then processing those pieces in parallel to increase the TPS. Layer 0 scaling is meaning to improve the scalability, optimizing the data transfer protocol of the blockchain, which does not change the architecture of the upper layer of the blockchain. For example, the Bell-X router logic architecture is commonly used to improve the scalability of increasing the propagation span of block between nodes. This architecture provides a block distribution networks to improve the synchronization of nodes by increasing the span of communication between them. Each node in the blockchain assigns the blockchain distribution network through the peer node provided by Bell-X router and uses peer node as the gateway between the blockchain distribution network and the upper layer applications. For the evaluation part, there are external tools and the exception algorithm help smart contract ensure security. The security issue of programming language can be only solved by the optimization. For the POW, it has better scalability, high delay, and high resource consumption. For the POS, it has good scalability and low delay, also low resource consumptions. Although trade-off for the scalability, security, and the decentralization of different application scenarios are made to allow blockchain preferences to meet the specific needs.